Tutti collegati, connessi? Dai ragazzi, apritela, aprite il video. Okay, I think it is possible to continue our workshop, and now a talk from Paola Letardi of CNR Genova, Istituto Scienze Marine, if I remember what is ISMAR. And now continue, and with multidisciplinary and the methodological issue about, I think, something regarding the corrosion, so the surface, and also from physical point of view, chemical point of view. It is very interesting because if you want to do a model, as you've seen before, you need data, you need to understand your data before you modeling. Okay, so Paola Letardi.
Thank you. Same time. Okay, I'm very happy that I had the chance to listen to Roberto Natalini, because it was really exciting for me to see all these kind of modeling of data. And I will focus my intervention on one peculiar problem, which is the conservation of outdoor bronze monuments. This is not very widely addressed in the scientific and conservation field, but I think that every one of you is clearly aware of the huge amount of monuments that we have in this field, mainly from Renaissance time, but also from the last part of the 19th centuries and the beginning of the 20th centuries, where we have a lot of memorial in bronze. And these kind of outdoor artworks suffered a strong effect from the acidification of the environment and all the changes that we had in the atmosphere during the Industrial Revolution. So also very old monuments like the horses of San Mark, for example, which are from the Roman times, suffered from heavy corrosion because the acidification of the environment makes patinas that were previously stable more unstable. And this study on the horse in San Mark is one of the first scientific study for conservation in the field of outdoor bronze monuments. And at that time started some kind of analytical investigation led by metallurgists and people working with metals in the industrial field. So with some tools that nowadays we look at is not very good. And since the very beginning, also the modeling, 3D modeling, in order to address static problems that you have with these big monuments have been addressed. So the story started at the end of the 20th centuries, and I will try to give you some evolution in this field and how we better understand the problem in this field, just starting from some experience that I have the chance to bring about, just working directly on the restoration of outdoor bronze monuments. At the very beginning, the story was just characterizing the degree of corrosion, because my background is in material science and technical analytical method developments. So at the very beginning, I focused my attention in trying to adapt electrochemical methods that were used in the metallurgical industry and in the corrosion science to characterize corrosion of metals, and try to adapt this kind of technique, which is the electrochemical impedance spectroscopy, to application for outdoor bronze monuments. Okay, so at the very beginning, we were just trying to better characterize corrosion rate on outdoor bronzes. But going on different restoration workshop, we realized that in order to understand what happens, we need several different analytical techniques. And the problem is much more complicated than knowing the corrosion rate and if coatings is effective or not. So I will try to give you a general idea of the problem. One of the main points is that when we deal with the outdoor bronze monuments, we have objects that stays in a changing environment. And so we need to conserve something that is evolving. And when we do measurement, we just make a photo, but we have to understand the film. So there are several steps where we can do measurements. There is the phase before when the object is under our attention, and we have to understand how it was done and how long was there, what happened before, and which is the conservation situation. Then we have to clean the surface, and we know that that surface is not stable, and so we have to make some coatings in order to reduce the interaction between the environment and the surface, and the statue will interact with the local microclimate, and this is a cycle, and we have to understand which is the time to make something more. During the time, we understood that the problem is very, very much complicated. We have a 3D objects. So different parts of the same statue are under different microclimate and can behave differently. We have an alloy. We have the results of the interaction with the external atmosphere, which make what corrosion scientists call corrosion layer, and what conservators call patinas, deposition. That there are different terminologies. And then we have the treatments and the history of the treatments and the past restoration intervention and the interaction with the atmosphere, which is changing. So the situation is very much complicated, and you need many different scientific background in many different fields in order to try to manage in this situation. I come from an institute who is devoted of corrosion of metals in atmospheric, so atmospheric corrosion, and there has been in the past many studies that try to have a gross idea of which is the intervention of materials in relation with the atmosphere, especially at the end of the past centuries, because the acidification was creating very big trouble, not in the conservation field, but just in every structure. I mean, metals are a kind of material that has been very largely applied during the 20th centuries, and the corrosion is a very big economic problem. So there is a lot of research in this field, and there was a lot of research trying to assess the risk according to the composition of the atmosphere. So this is a very big project that consider also the behavior of some material interesting for cultural heritage. but it was just bronze, which is a very generic term. And but this was important to make some risk map on a large scale. As Roberto told us before, then you have to go into detail, and the situation is something more complicated. But what is interesting is that there was just found some dose response function in order to give an idea of the corrosivity of atmosphere in a certain environment. This field is still of large interest in the corrosion community. And one of the points that I want to focus you is that there is a link between material science and corrosion, because if the tools of material science corrosion are interesting for conservation science, conservation science can give very important information to the material science community on the long-term behavior of materials that has been used, for example, for storage of nuclear waste, where you need very long range corrosion rate, and it is interesting for the copper use, which is very widespread in our life. So the corrosion impacts and the atmospheric corrosion is a wide field of research. And inside that field, there is some awareness of the importance of this research also for cultural heritage. There is research of new tools in this direction, but we have some problem. When I started in this field, we started just addressing the topics of coatings, effective coatings for adult bronze monuments, because the coatings that were used were not completely satisfied. And a lot of people working in treatments, coatings, and corrosion were starting projects for developing new coatings in this field. And we realized that there is a very big difference in these two fields. There are a number of standards for studying this field, but they are completely useless for corrosion in cultural heritage field, because usually methods are considering new materials, while for the conservation of cultural heritage, the surface layer that has developed during the time cannot be just removed, and that's all. So we understand that we need to consider patina under the coating, but we have no standard, no defined methodology to address this point. There is, since the beginning of this century, a group which is working on standards for conservation, but there is no standards in the metal for metal conservation. So one of the points that also Roberto addressed is that, okay, so we need coupon to test data, treatments, and so on, because we need a lot of surfaces. We need to know very well how they are, and we cannot do this on monuments because we have not enough surface, and because we cannot make tests on monuments because we can do damages. So what we need is working on coupons and asking which is the relation with real objects in all these time going. And the point is that we need some kind of measurements that can help us to make this bridge. So what we did is, to some extent, trying to work on portable, non-destructive techniques that would be used both on monuments and on coupons, and working also on studying the initial corrosion layer on different copper alloys in order to try to have a surface that was good enough for testing the treatments, because we need a lot of surface. We need a surface that is as similar as possible to the real object, but how do we create a surface that is similar to the thick crust corrosion layer that we have on real objects to test our treatments. To this end, we are just using the Genoa experimental marine station, which is used for corrosion testing, like the project I show you on at European level. And so here in this situation, we can follow the growth of the corrosion layer in conjunction with the climate parameters, the meteorological parameters, and with standard techniques. Doing this, we were able to focus that the different composition of bronzes, ternary bronze, quaternary bronze, copper, in the same environment was growing different kinds of patina. We try some kind of correlation with the weathering parameters that are monitored during the evolution, but it's too much work. So I have plenty of data if you want to make some simulation. Then point afterwards is how I map what's happened on coupons with what's happened on real artworks. At the very beginning, the course in St. Mark, there was sampling, and you were taking samples, but there are two problems. One is that conservators and superintendents and so on are not very happy that you go scratching, cutting, taking pieces, and at the very beginning you need a large piece to make this kind of analysis. The other point is much more critical, and is that these surfaces are really inhomogeneous. So when you are going to make sample in one point, which is the significance of that point for the whole understanding of the statue? So there has been, during these last 20 years, a very strong development in instrumentation for making non-destructive measurements directly on monuments. In the field of outdoor bronze conservation, now we have a large variety of techniques because we need to characterize many different properties of this surface. Optical microscopy and color give us some kind of information which are the more near and easy understandable for people working in conservation. The look, the aesthetic appearance. But then we know that we need also some physical properties, thickness, roughness, corrosion rate, the chemical composition. Really, we need a lot of parameters to understand what happens. And in the development of this field, we also now have this network where different instruments are, you can ask for different instruments, and the people who is able to use this instrument, because you cannot be an expert of all the techniques, and we are going to apply some more techniques in order to better characterize the chemical composition, the thickness of the different layer that we have on the surface, and the texture. The other point is the sampling, because obviously you cannot map all the surface of this very big object. So you need to define a way to make relevant sampling, and as the definition of the different measurements is not so precise, as I will tell you in a short time, the best way is just working by comparison. So you make measurements before the cleaning, after the cleaning, after the treatment, after sometimes that the treatment has been applied and you want to characterize how it's evolving. So you need to make a very good grid, which is simpler on a sample, can be much more different on an artwork, because you need some tricks in order to reposition exactly the instrument on the same point, because each kind of instrument, each kind of technique have the ability to sample a certain area. And so going on the same area for comparison reason is much important. We tried a deep comparison between coupons and the real objects in cooperation with Fonderia Battaglia and the Institute for the Science and Cultural Heritage in CNR during the restoration of the Memorial of Re di Puglia. This is a very simple case because the objects are 6,000 plates with the names of the soldiers died during the First World War. During the commemoration of the First World War centenary, there was a big restoration there, and they had to restore this huge amount of plates, which are just plates, so the simplest situation. And so in this case, there were, for conservation reason, the treatment was sandblasting, applying an artificial patina and then applying coatings. So we worked on coupons with the same alloy and we made the same sandblasting, the same artificial patina, and then we tested different coatings and we exposed to natural weathering the coupons, and then we go and made some measurements also on this place. The exposure was done in the station in Genoa in order to have all the parameters and making exposure in a standard situation. And we compare the data trying to focus similarities and differences, and there are differences. In a recent project, we try to get more into this kind of work, just defining a grid of measurements and defining different points with different measurements. And you see that we have a huge amount of data. And this is just a door inside the monumental cemetery in Genoa, and there are plenty of doors. There is some mapping of objects inside this Staglieno cemetery, but it's very difficult because you have different tools on the same objects which are not speaking each other. So it's very difficult to gather all the information. And what we did with the data measured on this bronze door is just trying to figure out which is the range of variability of the different variables according to the precision of the different instrumentation, and then how this evolves according to the treatments that is made on the tomb. And there are tons of data that you need to analyze and correlate. There are some tools in this direction, which is mainly in chemometrics that has been largely used in corrosion science and in chemistry applied conservation of cultural heritage in general. The application in this field are still very poor. There is some application of chemometric tools in order to trying to analyze spectra. I didn't spend much more time on saying that many of these instruments are giving you spectra. So each spectra is a lot of data, and you have many spectra on the same point in different times. So you need some tools in order to reduce the complexity. It's something like with the cinematic and thermodynamics. You need the average tools. So that there are some experience in this direction, and then you need some database when you can compare the results on your objects and a general mapping. So we also need to put together the knowledge because it's really complicated. So there is some experiment in this direction. The key point is that you need web-based application. There is some application in the analysis of this data because sometimes measurements are done on some kind of simplification. Your instrument is taking some physical principle and you get numbers making some approximation. But in cultural heritage, this is not always true. For example, X-ray fluorescence spectroscopy, the instrument is giving you a number considering that you have a homogeneous volume. But in the case of cultural heritage, you have thin layers, so X-ray can penetrate, and so the analysis can be quite difficult. And so Monte Carlo methods can help you to disentangle the spectra that you can get in this complex situation. Images, as I told you before, are useful to characterize the behavior, but then we need some maps that help us to identify from images to the corrosion layer. And I don't spend time in this because I think that you are more expert, but the data management is a very complicated issue with 3D models, with database on web-based application in order to make some common work, because you need many different people with many different attitudes and expertise in order to put in together all the stories. So just very quickly, I hope that I give you at least some spot idea, because every single point would require a very long description. But the feeling is that now we have a lot of the bricks that can allow us to put up the wall. I don't know how to describe, but we need many different people with very specific knowledge and tasks that can pull together in order to make together all the complicated situation that we have to face. And I want to thank you, a lot of people that from restorers and colleagues in different institutions that allowed me during this year to put together all this. Thank you for your attention.
Thank you. Yeah. As before, if you have some question for people here, come close to the microphone here, or people online. I have only to ask for when you spoke about the spectra, your data, you mean each spectra image. I mean, for each region of pixel, we have a spectra or something like that?
The point is that from a physical point of view, the spectra is that you are just in a point, and when you make a length, this is a scalar. Okay, but if I make some FTIR or impedance or X-ray diffraction, I'm just going to scan a range of a frequency, and I get the response of the system in a different range of frequencies. So I'm always making an excitation with some particles in a point, and looking to the response, and I'm varying the kind of particles I put in, frequency, energy, and so on, and going to look at the response. And the kind of the spectra is just which is the response for different frequencies, and according to the response, I know that there are some kind of fingerprints. So for X-ray diffraction, I know that brochantite has that fingerprint, cuprite is another fingerprint. So I make the spectra and I compare the spectra with the different fingerprints, and I can say, okay, here I have cuprite, I don't have brochantite.
Okay,
And this is true for different kind of spectroscopy. For electrochemical impedance spectroscopy, I give an electrical excitation. I get the response in frequency. In this case, I have a complex spectrum in which I have a real part and the complex part, which is as a function of frequency. And looking at the spectra, I can guess the corrosion rate. I can also have, there are some models that describe the porosity and so on. So each one of that data is a complex data.
Okay. Sorry. If there is some question here or online people.
Just a short question.
Yeah.
Because we are maybe out of time. But it's very interesting, and sometimes we work with data from right here, you know, because we have a collaboration group of Naldi in Sapienza with Barbara De Filippo, and we made an article about that. But the problem, a very big problem, is that it is difficult to measure the in-depth growth of the patina, because you have maybe a qualitative description thanks to this spectroscopy techniques, but to know if we have, I don't know, 1 micron, 2 micron growth of patina without cutting the signal is quite a problem. Do you see some techniques maybe useful to have this kind of assessment in the future? Because it should
I think that we have to reverse the problem. And we need to use different tools according to the problem. We study a lot the growth of this kind of patina, and what we did is just putting coupons and making measurements so we can follow the growth and we can understand how is going, that Wozniakive is going brochantite, and how at the beginning you have atacamite and not paratacamite, and nantocite is changing and so on. So in this way, we are just going to study the growth of this kind of patina according to the atmospheric parameters and trying to understand the mechanism in which this layer is formed. Our experience is that the big growth of these patinas is in the first couple of years. I'm not going to tell that 2 years are enough, but as you have this exponential growth, the first couple of years gives you the largest part of information. Then you have thicker patinas on real objects, but the mechanism are more or less that one. Okay. Then you need to study real objects. But for conservation problem, you know that the composition is more or less that one. Now there are 20 years that are scraping patinas from statues, and I can tell that more or less the main features are that one. So for conservation, we can rely on the main features. If we have to modelize, then we need the mechanism. But I think that mechanisms are not going to be studied on real objects, because there you have too many parameters, and if you don't make some kind of simplification, you are not able to make models. This was what they told me when I was studying. I don't know, but I think that this is one of the problems.
Okay. Some other question, or please go here.
Thanks a lot.
I will say more than 1 minute.
Yes, exactly. Stay back. So I have to maybe at some point not to ask so many questions. But about your reticular plate, which I like because there's still no geometry in there. But there is still some. Do you have the so-called microporosity of those? Do you know the surface?
Okay, we use just a portable rugosymmetry for the surface of the blades.
Yes.
While on coupon, we use the same method, and then we put also the sample on a microprofile, okay, in order to. But and we have a lot of data. It was just a basis.
So the big variability between the plates?
There is a big variability, so that data can be quite different, and we, as we were in a hurry because of the restoration was going on, and we had to give responses, we saw that we were not able to obtain the same rugosimetry, average rugosimetry on the coupons with respect on the plates. We didn't get into detail of this because we needed to run and test coding. So we say, okay, we know that the rugosity is something different from the coupons and the plates, linear rugosimetry with the portable rugosimetry. Profilometry has been used and developed from another institution in CNR. We are going to use this portable profilometer on the Tombe Miecco in the next month, and we are going to go deeper in the differences of the different measuring methods and in the definition of the real parameters, because as long as you compare data with the same instrument, you have a trend and you can tell what's going on more or less. But if you want to make models comparison in different situations, you have also to address the agreement between the different instruments and the definition of the parameters with respect to the kind of instrument that you are using to make measurements.
Sorry. So thanks. We'll talk probably later on. So you have lots of data. This is
for sure.
Thank you. So I think now thanks again to Paola Letardi. And now the next speaker is Antonio Bilotta from University of Calabria. And now, after more chemical-oriented and environmental-oriented talk, now introduce a new actor because you introduce mechanical properties, structural mechanical properties. So we have more multidisciplinary aspect, okay, from chemical, mechanical, and so on.
Thank you very much.
Thank you.
Perché lo stesso. Good morning, I am Antonio Bilotta from the University of Calabria, and come parliamo in Calabria, diciamo più calabrese. Ok.
Volevamo dire.
Vabbè. Ma devo usare il microfono? Okay. This topic is about the which okay. Okay, do you hear me? No. Okay, okay. I started to work with my colleagues that maybe you know better than me. There are Margherita, Andrea, and Emilio from Università Sassari. I started to work on this topic with them some few years ago. It was a research program about the historical buildings located in near Sassari, Porto Torres, in fact near Alghero. And we, in that experience, we worked with the use of laser surveys to build the computational models to be used in the static analysis of this kind of building. Now, our interest is still in this subject, and with this talk, I would like to talk to you about the computational procedures that we can try to devise in order to make the process of the analysis of historical buildings more more quick, also more computationally based. And to start with this topic, I would like to talk about how this problem is tackled in Italy by engineers usually. In Italy, we use Italian codes, and there are also other instruments that are based on these codes. But we think that if we want to face with this problem, we have also to compare our approach with the usual methods adopted by engineers in order to assess the safety condition of these buildings with respect to vertical actions or horizontal action, for example, seismic actions. In particular, I'm sorry for some words that are in Italian because they are taken from the Italian code. In particular, the Italian code, with respect to existing masonry buildings, requires 3 levels of investigation. One limited level with only some geometric surveys, also other kind of surveys. And this investigation can be deeper and deeper if we arrive to the LS3 level of investigations. But if you read the words, it's very difficult to find a clear quantification of what is required. It's mainly a qualitative description of the survey. For example, you can see that is not clearly stated that you have to make a mechanical experience, a mechanical test on these materials. It's very hard to find a reference of this kind. After this, always about the masonry existing masonry buildings, the Italian codes give a classification of the masonries, starting from the chaotic masonry, finished to the regular one, and on the basis only on a qualitative description. For example, look at the first one, masonry in chaotic stones. And on this basis, you can assign the mechanical properties like compressive strength, shear strength, Young modulus, shear modulus. Okay, the only reference that we have to some mechanical ingredient of this survey we found at the bottom of the slide, because the Italian codes require only that mortar at least must have a compressive strength between 0.7 and 1.5 Newton over square millimeters. And this is the only mechanical requirement. On the other, for the other part of the description, you see only kind of geometrical description, but is a qualitative kind of description. It's not, there are no kind of measures or parameters. It's also possible, anyway, if you have some further information about the masonry. For example, if you know that there is a good mortar, or if you know that there are horizontal bed joints and so on, you can eventually also upgrade the mechanical properties by applying these coefficients, these multiplicative coefficients. A more elaborated approach to the problem is represented by the abaco delle murature masonry abacus della regione Toscana. In this abacus there are a collection of sheets that describe some kind of masonry that are analyzed by engineers or by also some organisms like province or region. And you find 142 masonry sheets. And in each sheet, you find geographic position of the building, building's age, number of floors of the building, position of the wall analyzed, masonry texture survey, photos, drawings, and also the classification of the masonry with respect to the Italian codes. But in order to try to go further with respect to the Italian codes, in this abacus is proposed also the use of experimental tests that are shown here. If possible, you can also perform some experimental tests on the masonry. However, these kinds of tests are not possible to be used on historical monuments, but it's only the only place where you find the suggestion to use some experimental tests to evaluate, for example, compressive strength or shear strength and so on. And in this way, you can use some mechanical properties that are different than the one proposed in the Italian code. At the end of the sheet, you can find also the conclusions on the masonry, and you find the main mechanical properties that you can deduce from the analysis that are presented. But more interesting, in this abacus is also present another kind of a qualification. This qualification is based on the quality masonry index that was proposed by Bordi and De Maria. It was updated recently in this work, and is also a tool that can be used to understand better the mechanical behavior of the masonry, or at least to understand which is the level of knowledge that Italian engineers have about masonries. This masonry quality index essentially uses some parameters that are written in blue: horizontal bed joint features, wall leaf connections, stone brick shapes, vertical joint features, stone brick dimensions, mortar mechanical quality, stone brick mechanical quality. So at these features, you can give a vote to these features and say that, but the vote is given only with this word, for example, not fulfilled, partially fulfilled, and fulfilled. So if have that the horizontal bed joints is not a parameter that is fulfilled, you have to assign 0. Is partially fulfilled, you have to assign 1, and if totally fulfilled, you have to assign 2, and so on. On this basis, you can obtain this quality index that is not the simple sum of these numbers. There are some formulas that you can use to obtain this number. And you have also 3 numbers. One number for vertical actions is no. And okay. One number is for vertical actions. Another number is for horizontal actions. And another one is this action that is transversal to the plane of the wall. Usually, engineers think to masonry constructions as the assemblage of walls. So they think to masonry like a two-dimensional, from geometrical point of view, two-dimensional problem. Okay. And on this basis, you can to give a quality evaluation of the measurement. In this work, they obtained also a correlation, for example, between IQM for vertical loads with respect to compressive strength. They verified that there is a good correlation between the compressive strength and this quality index. The same for the quality index for horizontal actions. There is a good correlation between this index and the shear strength. So they found that there is, however, also these numbers are also talk about quality. It is not a quantified measure about the measuring. There is a good correlation. Okay. Now, given this huge experience that, however, we have knowledge, data, experimental test, and however, as we saw, there is a very loose link between the mechanical evaluations that the engineer does with the quantitative information. There is only in very few points you can find a very sharp indication about how to evaluate the mechanical property of the masonry. So it is possible to build a masonry abacus based on computational evaluation. So make a similar work that is present in this abacus of Tuscany region, but base this abacus on computational models. In order to start, I would like to remember to observe this. On the left, we see what say Italian codes about the kinds of measure that we can have. On the right, we see the parameters that are used by index quality, measuring index quality index. So if we observe, we find that there is a lot, the 80% or 90% of the words that you see in these two texts are about geometric parameters, and only and a little part is about mechanical parameters. In this respect, IQM is more sharp in this distinction, because we find a clear distinction between geometric information and mechanical information. On the other side, Italian code is not so sharp because, for example, say pietra tenera, I know the English word for soft stone. In order to characterize the mechanical behavior of the masonry, we talk about the soft stone, so a very generic definition. The only place where Italian code talk about mechanical information is only about this word, a good mortar, but always good mortar, not a good mortar. Okay, but this is the point that we can use to start this proposal, and we see that it's very important to give importance to geometric description of the masonry. So let's talk about how we can describe materials when we want to make a computational mechanical analysis. There are several methods. We can start with a description of the inclusions inside one material. We can think to masonry like a matrix, and the general matrix is mortar that includes some stones or bricks or blocks, And this description can start from the inclusion, and we can use, for example, manual measurements, image analysis, stereoscopic image analysis, Fourier analysis, tomography. Also, you can also, if you want, make a tomography of the. It's possible. This approach is used for small cubes of concrete, but it's possible to use this kind of approach for large buildings. Anyway, another way to describe the geometry of these complex objects is to generate this geometry by simulation. For example, there is in this kind of approach, there is a first phase that is called the picking phase, in which you choose the shape of the inclusion, choose how many inclusions you want to insert in your description, and then after that you have to insert this inclusion in order to obtain a geometrical description of the material geometry. But this approach is has some weakness, because, for example, there is here another approach, the implicit function approaches is another way to obtain this kind of geometries by simulation. In this kind, the approach has also the approach that we saw before. There is a problem that the geometry is not completely morphologically controlled. We have a loose control on the final result. You can control easily the percentage of the inclusion with respect to the global volume, but to control the shapes is not so easy. On the contrary, in the case of the masonry, we want to control the shape of the inclusion because it's an important information. We saw that we have to describe if there are horizontal bed joints or vertical bed joints and so on. And for example, we can start, the simplest approach is to use the manual approach. Simply you have a wall, masonry wall. Then you can start by drawing by hand each polygon surrounding each stone in the wall. You can go for all the stone, always don't make this kind of work for all the wall, but you choose some representative volume, representative area of the wall. You can also choose more of these representative volumes. It's okay, the same. And then you, from this construction, you can obtain a geometrical description that can be used after in the mechanical analysis, for example. And this is the manual approach. Or you can also use image processing, like thresholding. You can go from the colored image, RGB image, and go through some passages, go through the final geometrical description in order to obtain this description that is useful for the analysis. Image processing is only a subfield of the general instance segmentation. Instance segmentation is a general approach that can be used in order to automatically to find the instance of the object that we interested in. For example, when we see some example from this wall, you can obtain the polygonal description of each stone that run on the wall, same in this line. In general, you can also, but this approach is very popular in this moment because it is used in general in artificial intelligence application. Is a typical application, instance segmentation, in order to detect inside photographs some objects. For example, in this case, we start, these approaches are more powerful because, for example, you can start from a very dark image, very bad image, and the same you obtain the results that you want. In our case, maybe we are more lucky because if our picture is not good, we can repeat it. It's not, you can also repeat. Okay. And this is the geometrical part. Let's go to the computational, to the mechanical part. And let's see how we can build the computational mechanics models that you can use in this kind of analysis. We have our geometry. We have in our geometry the blocks or stone or bricks. We have also the mortar, and we have to assign a mechanical model for each component in order to obtain at the end the mechanical model of the masonry. For example, you can use for stone and brick, you can use a rigid block model. You can use a rigid block with fixed cracking planes. You can also use linear or non-linear continuum. You have several choices. The literature about this topic is very huge. It's only a problem what you want to choose, to make this kind of analysis, and what you think that is better to do. And then there is the mortar model. When we talk about mortar, it's more about an interface between two materials. So often you talk about how, which kind of interact. It's in general, it's an interaction between two blocks. That is in which you find also the presence of the mortar. This is the correct way to see this kind of mechanical interaction. And for this, you can use a nonlinear interface model, or you can also use nonlinear continuum, or use nonlinear continuum, linear or nonlinear continuum with embedded nonlinear interfaces. After this is usually this level is called also micro level, because it's about the single components of the masonry. After, we have to go to the analysis of the overall building. Okay, in order to perform this kind of analysis, you can choose several ways in order to bring the micro mechanical response, the information that you have at micro mechanical level, to bring this information at the structural level. You can also use directly the micro model. With this choice, if you have the computational power required, you can describe all the stones of the building. Okay, it's theoretically possible, but not so feasible. Anyway, you can also use a priori definition of the homogenized macro level mechanical response. So there are several techniques in order to transfer the micro mechanical behavior to a macro response that is about a unit cell that is it is a representative volume element of our macro model. Or you can also perform a concurrent computational homogenization. You can maintain both levels, micro level and structural level, and to make an analysis that is that go together. Anyway, we need some mechanical information in any case, because also if we use a micro-mechanical model for brick, micro-mechanical model for mortar, we need some experimental information, but we can use not so destructive tests. For example, we can use this drilling resistance measurement system. We have to use this drill, and there are some correlation curves between the force that you use to make the drill, to make the hole in the material, and some mechanical properties. For example, here is the compressive strength, this is the dynamic modulus, and other properties. Okay. However, it's not, this approach is possible, but it's not anyway so easy to be applied, because I don't think that this is only a picture. The man didn't make really the hole. I don't think so. It was not a picture, in my opinion. However, this is a way to avoid big destructive test. Another way is we can think to compressive testing applied to simple specimens, to small specimens of the material. This is possible. Also, in any case, some small specimens are required. In this way, you can obtain a lot of information: elastic modulus, compressive strength, predicted post-peak corrosion effects, fracture energies, and so on. But also this kind of test can be avoided using ultrasonic evaluation. Okay. For example, you see here some correlational curves between the ultrasonic propagation velocity with Young modulus, tensile strength, compressive strength, and so on. However, these correlation curves must be obtained before. There is a point, these curves were obtained because several usual tests were performed, and on the same materials also they performed the ultrasonic test. And this way they found the correlation. So if you have a new material, maybe that you don't have this information. So ultrasonic test can be not always can be applied. Also, you need information about the interface. So the sliding, the properties, the mechanical properties of the blocks with respect to the sliding, so with respect to the interface. Conclusions and tangenta. So, which is the typical computational procedure that we use, for example, to build a database of masonry sheet, in which there is, however, a computational evaluation of the mechanical properties of the masonry. You start from the masonry, obtain a geometric description. In this geometric description, you have to insert information about, you have to choose a model, a block brick model, on the basis on very limited experimental tests. The same is for the mortar. You have to choose an interface model starting from some tests. And then with this information, you can simulate actual experimental tests already available in order to obtain what is considered the mechanical properties for the machine. For example, compressive strength, tensile strength, or Young modulus, shear modulus, and so on. This is, however, also an ideal situation, okay? Because it's also possible that you can also go from this information from the right to the left in these arrows, because you can also use, for example, the information, the experimental information that you have from this kind of test in order to improve the mechanical response that you obtain through your model. Okay, so it's not only in this direction that works this kind of work, but in some cases can work also in this other direction. And in this way, it's possible to to obtain. There are a lot of information about masonry. For example, in Abacus or in Tuscany regions, there are more than 100 masonry sheets that there are a collection of data information where it's possible to test, to try to devise a computational based classification of the masonry. Okay, this is the end. Thank you very much.
Thank you. Yes, there is some delay.
Okay.
So a very fast question. Whoever. Okay.
Thank you.
Now, audio curiosity. Which kind of nonlinearity you consider? Because larger formation, plasticity.
Plasticity, and at this level it can be also at the big small displacement, because we are talking about the first phase of the mechanical response. However, you can also change on the, if you want, for example, to simulate the dynamic action. For example, it's important to simulate the dynamic action of one single panel, because you can see if there are some explosive behavior in measurement. With dynamic action, very often the link between each stone is not so strong, and so you can also that you do not obtain a global response of the panel. So you also have to, in this case, if you want to test this kind of behavior, you have to use some other models. For example, particle methods that where you consider large displacement and you consider dynamical action in a proper way.
Thank you. So thank you again.
Thank you very much.
Okay. The last speaker, I apologize for the delay, but Francesco Freddi is very interesting because chemical, mechanical, and now I think chemical-mechanical properties of materials. So I think it's very, very interesting to have this talk at the end of this.
I hope so.
Francesco Freddi from University of Parma.
I'm just asking if you can see me and hear me and see my screen. Can you hear me?
Yeah, okay.
Right.
I think I have to close this one. Okay, so if you can, I can start. Thank you very much for the invitation. Sorry for not being there. I will try to recover sometimes because I think we are a little bit late. So just the title is Cover Cracking Carbonated Reinforced Concrete Element, a phase field approach, and this work has been done in collaboration with a PhD student, Lorenzo Mingazzi of the University of Parma. So this is how the outline, motivation and objective at the beginning. After that, I will move to physics and try to describe the three main phenomena that govern the cover cracking in concrete: carbonation, rebar corrosion, and fracture within concrete element. I will just illustrate some numerical examples. First of all, validation and some simple cases in order to see the capability of the predictive model that I'm going to illustrate to you. And finally, some remarks. So, first of all, some features that may be interesting. Concrete is the most widespread material used in construction and infrastructure, but I think that there are also some piece of art made of concrete. So that I can see you, I've shown you some example. We have got a funeral tomb. Okay, sorry for the dark image, but there are also a Stadio Flaminio that the visitor abandoned. It's a very wonderful concrete structure that is this Spanish monument that is, I think, is not so beautiful, but there are some structure that is an example of the idea of construction that meets aesthetics, and this is the example of the bridge of Basento. It is in Basilicata near Potenza. It seems that a very strange shape, and it seems like more a skate park for the tricks of Tony Hawk rather than a classical bridge. You can see here it's another images, but I think that this is a piece of art that deserves to be preserved. So let's move to serious things. The corrosion is the most dangerous degradation phenomena of a reinforced concrete structure, because apart from the aesthetics, it affects the integrity of structure and structural element, because there is an important reduction of the bearing capacity of the structure, because the main phenomena at the mechanical level are the loss of utility of the metal, reduction of the bond strength between the two elements that is crucial for the correct mechanical mechanism stress transfer between the two elements. And another important phenomenon that is the swelling phenomenon of the rebar that leads to concrete cracking and spalling of the concrete cover that is extremely important to protect the bars from environmental condition. So the object is to present a predictive model that can describe, at least at the microscopic level, the cracking corrosion of bar. And the images that you see on the right of the screen are just some examples of rebar corrosion taken from some bridges. Let's move to physics. The main aspect of the problem, first of all, the carbonation, because concrete is a porous material where many pollutants diffuses, but for the case at hand, the most important is the carbon dioxide that reacts with the calcium hydroxide, and calcium carbonate is created. Apart from secondary effects, the calcium carbonate reduces the pH value, and this leads to a depassivation of the rebar. If water and oxygen are present in the neighborhood of the bar, the corrosion process starts. And there is an oxidation of the rebar. There is two main effects: the reduction of the reinforcement area and the generation of rust deposits. The rust deposit occupies larger value than the integral material and the corroded material. So there is a swelling phenomenon that leads to overpressure in concrete element, and at the same time tensile stresses in concrete that are extremely dangerous because concrete material is extremely weak to tensile solicitation. So cracks initiate and propagate within concrete element, and this leads to a speed up in the carbonation process because there is a free way for CO2 to penetrate within the element. And these are the effects at the microscopic level within the concrete element. There maybe appear some cover spelling or delamination that removes, in the two cases, the concrete cover. Some chemistry. This is the reaction. So CO2 reacts with the carbon dioxide and calcium carbonate is produced within the concrete pore. A secondary effect that effects that appear within concrete are pore clogging, because calcium carbonate is less soluble and occupies larger volume compared to the calcium hydroxide. So there is a lower porosity in the element, and there are also changes in the mechanical properties of the concrete itself. In particular, there is an increment of stiffness and an increment of strength. These variations are taken into account in the model. I consider in the simplest relationship and a linear variation of these properties, the porosity and the two mechanical properties, stiffness and strength, in function of the calcium hydroxide concentration with respect to the beginning. but the most important thing for this problem is the reduction of the pH. Now let's move to some equations that are for mathematicians. For what the diffusion of CO2 and reaction within the concrete element, I'm considering a classical reaction diffusion equation based on the Fick law. The diffusion coefficient is a function of the relative humidity and the porosity of the concrete, but also on the damage state. So where crack is fully evolved, I think the diffusion is very, very rapid. After, there is also the reaction rate. This is a function of the concentration of the CO2. Two reaction equations are considering for determine the concentration of the calcium carbonate and the calcium hydroxide. And also, is it possible to determine, starting from the concentration of the calcium hydroxide, the position of the carbonation front. So I think I have no time for many details. So sorry. From the concentration of the previous elements, in particular from the concentration on calcium hydroxide, it is possible to determine the pH of the element, and with simple, basically, relationship with the pOH, is it possible to determine the pOH and the concentration on the OH element, because these are crucial elements for the corrosion process. In fact, usually, due to the alkaline environment, the bars are passivated, so the phenomena of corrosion is very, very, very slow. But the carbonation process reduces strongly the pH value. And for value of pH smaller than 9, there is a depassivation with the creation of adjacent anode and cathodic elements, and a creation of a current from the anode to cathode. There are two semi-reactions, anode oxidation, that is written here, rather simple, and a cathode reduction, and this is the complete reaction. And in case water and oxygen, as I said before, are present in proximity of the bar, the corrosion process starts. And I've just considered an electrochemical model. And considering the stoichiometric coefficient of the corrosion reaction equation, is it possible, starting from the concentration of H, to determine the iron that is consumed, that is interested by corrosion? I evaluated the electric potential of the two semi-reaction via the Nernst equation. And after that, is it possible to determine the corrosion potential and the current density via the Butler-Volmer equation? And this is a clear definition of the intersection between the two semi-reactions, so the iron dissolution and the oxygen reduction. And this intersection gives you, in this Evans diagram, the current density and the corrosion potential. The current density value permits to determine, via the Faraday law for electrolysis, the changing radius of the bar and the metal elements. So starting from the initial position and the initial radius of the bar, is it possible to determine the expansion in the bar? That is the crucial element for determining the initiation and the propagation of crack within the concrete element. So once the expansion and the swelling is determined, the fracture process has been studied with a smeared approach. I don't know if you are familiar, just a few words. The sharp approach to fracture is extremely complex because the most difficult thing is the position of fracture that is unknown. So it's much more easy to study, especially from the computational point of view, this problem, PI phase field approach or the damage approach. It just a second field is introduced that defines the state of the material. 0 is sound, 1 is completely broken, and there is sharp transition between the two, and this red portion is the crack. So the solution is obtained as a two field functional composed by two energy terms, one associated to the strain energy density of the material and the other two associated to the fracture energy of the solid, of crack, sorry. These are the ingredients of the recipe for the phase field approach to fracture. So I'm just considering asymmetric behavior of the concrete because it's much more weaker in traction rather than in compression. And I'm considering a decoupling behavior of the deformation, elastic and inelastic deformation, in order to keep into account the swelling of the bar. So this is the expression of the strain energy of the bar, and this is the expression of the fracture energy of the cracks. And this is the complete expression of the function. So I think that I've spoken a lot and I've said a lot of things, so it's better to sum up everything. So for each time, I'm solving these three problems. The carbonation. First of all, I'm solving the diffusion reaction equation in order to determine the concentration of CO2 within the concrete element. The concentration of, after that, I evaluated the concentration of calcium hydroxide and calcium carbonate, evaluate the carbonation profile, and determine the pH within the concrete. If this is greater than 9, I think corrosion for me is not starting, so I go on with the carbonation process. Otherwise, if the pH has been reduced a lot from the carbonation reaction, so corrosion starts. So I calculated the anodic and cathodic potential via the next equation, calculate the corrosion potential, the current density via the Butler-Volmer equation. After that, I calculate the swelling, so changing radius of the bar and the swelling deformation. After that, I've solved it in an iterative way via an alternate minimization algorithm, the mechanical problem to determine the crack pattern within the solid. First of all, we try to validate the carbonation and corrosion phenomena that we are trying to describe. So we just compare our reaction diffusion solution with some experimental results and other numerical models. And we just compare the depth of the carbonation front. And we can see that, especially with the experimental data, we are not so far from that results. Obviously, we are just comparing the carbonation layer depth. After that, we try to see if the corrosion density that we obtain is in agreement with the results obtained from literature via experimental results. And so we have found that with our approach that is only based on electrochemical equation, we catch correctly the asymptotic current density value as the corrosion process has been evolved. So now I move to some complete problem, very, very simple cases I'm going to study. This is a bar that is near a corner within the concrete element. So these two sides are fixed, and CO2 penetrates along these two other borders. And the parameters that I've considered are taken from literature. The simulated time is about 20 years. And here I'm reporting the numerical results in terms of CO2 concentration, the carbonation front position, and the damage state. So you can see that CO2 diffuses within the solid. There is a carbonation front that penetrates within the concrete element. You can see here that here there's the bar that is not interested by the carbonation, obviously. And as the carbonation front reaches the bar, we will see that crack initiate and propagates and cut this corner very rapidly. And at the same time, you got the diffusion that within the concrete element that is extremely rapid. I'm considering different boundary conditions in order to see if this in some case may influence. So this is a very simple case. A small notch is considered along this horizontal border. And the solution is certainly influenced by the presence of these heterogeneities along the border. You can see that the carbonation front is deeper here. And the carbonation front reaches the bar starting from this notch, and the crack path is also influenced by the presence of this notch. And the last example, I'm considering 3 bars within a concrete element, just to see if the crack pattern may be different. And the CO2 diffuses along these borders as before. And this is always the solution in terms of CO2, carbonation front, and cracks. You can see initiation starts at this bar that is near the corner. After a certain point of view, there are cracks that connect the bar, that there are, in some cases, they interact, and there are some cover spelling and also a delamination of the cover. So I'm going to conclude. So the model that we developed obviously take into account several things, especially the environmental condition, the changes of the material properties, the rebar swelling, the carbonation, and the phase feed approach provides and permits to determine that crack pattern that in some sense are reasonably and in accordance with experimental results. But I think that this is only the first step of a very, very complex problem. In particular, it is crucial to compare the results and to fit the parameter of the model with a very, very intense experimental campaign. The model should be strongly improved, for example, by introducing the rust layer as a third material, because the mechanical property of the rust layer is certainly different from the pristine steel. And I think that also other effects should be taken into account. For example, the concentration of oxygen and the presence of water, humidity, water, and also the temperatures should be taken into account, because these parameters strongly influence the reaction of and the corrosion. I think also from the mechanical point of view, there are some improvement that should be taken into account, because in a model, the impenetrability condition is not perfectly fulfilled. So I think there are some crack pattern around the bar that was not so correct from my point of view. And in another way, in another direction, that this is rather ambitious, obviously, another corrosion that is extremely important and dangerous in reinforced concrete structure, especially in pre-stressed concrete structure, is the pitting corrosion due to the diffusion of the chloride ions, because this corrosion is extremely subtle, because whereas the corrosion due to the CO2 is evident, the pitting corrosion may be hidden within the concrete element, because it does not lead to the expansion of bar, but only a reduction of the reaction of the area of the reinforcement that may lead to a sudden collapse of structure. So I've concluded, and thank you very much for your attention.
Thank you. We are with some delay, but I share some. I have a very naive question. So, because there is some constraints in some part where it's possible to control the geometry of the cracks. I mean, for example, the length, something like that. The penalization, for example, for the length of the cracks, something like that. So for the geometry of the cracks, there is something which is possible to control, or there is some penalization in order to avoid some physical cracks. I mean, too long, something like that.
I think I've said it on the in the conclusion. I think there are some unilateral conditions that I should introduce, because there are some crack patterns that for me are not physical. Perhaps I've stopped sharing the screen, so I try to, if you can see here, I think at the end you can see the rupture around the bar. I think it's not physical, because there are some unilateral condition that is not correctly fulfilled. For what the shape of the crack, I think I haven't got any constraint. It just comes from the minimization of the functional, where the crack pattern is completely unknown and is given by the evolution of the damage parameter. I don't know if I answer your question.
Yeah. If there is no other questions from our phantom people or online, but I don't know. If not, thanks again to Francesco, also the speaker of his morning. Also, I don't know if there is some announcement, but I think we can start at 2:30. Okay? Sharp. Okay. Thank you.
What about the lunch?
The lunch is main lunch here on the floor. Io posso chiudere l'aula, quindi se voi volete lasciare anche il computer, volete.